Hi and welcome to Profex Tutorials. In this episode I'm going to give a brief overview of the user interface of Profex, and then we are going to process a dataset and try to identify the faces in the sample. This is what the Profex main window looks like right after installation and setup. But before we begin, we need to download a raw dataset from the Profex website. So I go to profex-xrd.org. On the page Tutorials, I select the First Steps Basic Refinement tutorial, and here I can download a raw data file right here. I need to extract it. And I will move it to a new folder. So now we can open this raw data file in Profex. For example, going to the menu File, Open Raw Scan File. I navigate to my Downloads folder, to the example dataset, and now I have to select the correct file format. It's got the extension RAW, but there are several different file formats using the same extension. So one is from Bruker RAW, but there are others, for example, Rigaku RAW and Stoi RAW. And it is important to select the correct format. If I assume that it is the Rigaku format, I can open the file, but I will get an error message. No import filter found for this file. So it's not a Rigaku RAW file, and in fact it was measured on a Bruker instrument. So I have to select Bruker RAW format, go to Downloads, and now it works. So this is just an inconvenience. Several instrument manufacturers all use the same extension, RAW, but in fact these are different file formats, so we have to choose the correct format. We can also open the file just by drag and drop. So I close this project, and instead of using the file menu, I can just drag this file here, and then it will auto-detect the correct file format. So now I don't have to choose between Rigaku, Stoi or Bruker RAW files. Now let's maximize the Profex window, and now we can see what's going on here. In the central area, we see the diffraction pattern, or the graph or plot. With the mouse, with the left mouse button, we can zoom. With the right mouse button, we unzoom. The scroll wheel zooms horizontally. And if we hold the Control key and use the scroll wheel, we can zoom vertically, and always use the right mouse button to unzoom. If we go to the Help menu, there is one entry, Mouse and Keyboard Commands. It opens a window that lists all the actions, the mouse and keyboard actions we can use on the graph here. So left mouse button zoom, Control and left mouse button. If we zoom in, we can drag. And the scroll wheel, for example, zoom horizontally and so on. Now, if we use the right mouse button on one of the axes, the X or Y axis, we get the context menu, and we can change the scaling, for example, on the X-axis. So instead of a linear scale, we can choose a square root scale or a logarithmic scale, and also zoom to, for example, the minimum intensity, which is somewhere around here. So we get a better zoom range, and go back by unzooming and to switching to linear scale again. On the X-axis, we can toggle between a D-spacing scale in angstrom or the more common 2 theta scale in degrees. On the left side of the graph area, we can see the list of open projects. Every scan file we open will create a new project, and we can show some more information on this project by clicking on the arrow here in the tree view. It shows the file name. Let's drag this a little bit. The file name, the file path, the type of project. So this is set up for BGMN, and the sample ID we entered when we programmed the data collection. Here on the second tab, plot options shows all scans stored in this file. So in most datasets contain only one scan, but it is possible to have more than one scan in one raw data file. In that case, we would see all the scans listed here. And all these lists and windows arranged around the graph area can be rearranged. So for example, we can change the size of these lists by grabbing here, and so we can see a bit more. We can also grab them by the title bar and move them around, and either let them float somewhere over the main window or maybe on a second screen, or we can dock them again to the side. So now instead of stacked windows, we see them on in a vertical arrangement. Or I can also dock it somewhere else. As soon as I approach the outer area of the main window, I will get notified about the dock area. So I can also dock it here. So it's very flexible. I can freely arrange these windows, and I prefer to have my projects list on top, the plot options here, and then the graph showing the refinement convergence progress down here. Another important window is the Refinement Protocol, usually shown on the bottom left area, and it will show the output of the read file refinement. So now it's just an empty window. And on the bottom right side, we will see the refinement results. It's called Refinement Parameters. It will show the refinement statistics and the phase quantifications and the refined structural parameters. There are more windows like this, more modules or dock windows. They are all listed here in the window menu. For example, one that shows the chemical composition. So this is stacked down here. It's still empty because we don't have any refinement results yet. The context help is quite important for new users to get some information on the refined parameters. And whenever we close one of these windows, we can always open them again from this menu. So the context help and the refined parameters. The first thing we want to do is, if we process a dataset, we need to know which phases are present. So we need to identify the phases that were measured before we can start with a read file refinement. And in Profex, we have several options to do that. The easiest would be to just scroll through the list of reference structures, but now the entire database contains more than 700 structures, so it would take quite a while to identify the correct phases, and that would be a bit inconvenient. So the next possibility is to double-click on the strongest peak, and now it will show us the 5 phases which have their strongest peak closest to the double-clicked position. And now we can decide, so the first one is loaded in the reference structure list. Now we can decide, is any of these reasonable, maybe from the chemical composition or from the geological situation. We have to decide, does it make sense what we see here or not? So maybe we can just try and double click the second strongest peak here. But we also have to compare the green line positions with the measured peaks. And this doesn't look so like a very good match. So the first one, maybe the second one is better. So we can type here TCP, this one. And this actually looks like a pretty good match. So it's perfectly matching the peaks we measured. So it seems to be a tricalcium phosphate with some sodium. But let's use the third approach. So this might work if it's an easy composition, if we can, if we have well-defined peaks, not too many phases, not too much peak overlap. The most powerful and usually most successful method to identify unknown phases is the search match module. And I will first close the context help window. And the search match module is one of these dock windows here in the window menu, search match phases, and it will open usually on the right side of the graph. And we have 4 pages to set up the search match process. And usually we go from the left to the right, and at the end we will see the results. So on the first page, we have to decide among which phases we want to search. As I said, there's a total of 808 phases in the database. So if we search among all of them, it's going to take quite a while. The search match process is relatively slow. So it makes sense, just to save time and to improve the score list, to limit the search to a certain subset of phases. And as you can see here in the default BGMN template structure, the phases are categorized in directories based on their chemical composition and on the type of materials. So for example, we have ceramics for synthetic materials, we have minerals for natural materials, organics, and some special categories like phosphates, silicon carbides, metals, alloys, oxides, and so on. And there is one folder with named BGMN. These are all the minerals that were, the structure files that were created by the BGMN developer team, and all the others were created by myself. So in this case, this is a synthetic sample. It's a mixture of calcium phosphate ceramics. So since I already know that from the synthesis, we can just search among all the phosphate samples. That will only search 73 phases and will be much, much quicker than searching among all 800 phases. So I just check this subdirectory. Up here, we have to select on which scan we want to run the search. So in this refinement project, we only have one scan because I removed all the others here from the plot options list. So if there were multiple scans in this project, I could choose on which one I want to search. On the next page, I can apply some chemical restrictions. This is a new feature in Profex 4.2. It's not available in the older versions. And this is a pretty standard feature. It works more or less the same in all search match programs. So from the periodic table, I can check each element. I can, for example, force it. So I only want to search phases that contain calcium. For example, I want to discard all the silicates, so I click 3 times, it toggles from green to blue to red and back to optional, so I want to have this red, but I want to search all the phosphates, so I can further restrict the chemical composition and filter the phases to search. Again, this just helps to speed up the process of search match, and to have a really, really strict filter, I can also check calcium phosphates. And with this button, I can toggle all the gray elements to discard. So this is a super strong filter. It will only search among the pure calcium phosphates. Maybe I want to have the ones with OH groups or the hydrates as well, but optional. And to make it a little bit more flexible, I could allow it to contain magnesium also, and maybe sodium, potassium, strontium. So now it has to contain one or more of these, but it has to be a phosphate. So this is a strong filter. It can be it can contain hydrogens or OH groups or water molecules. On the third page, I have to select the instrument that was used to measure this data set. In this case, the instrument is called RMS D8 ADS 15 Lynxi XE. This is the configuration specifically for the instrument, and for the setup of this instrument I used to measure this data set. And we will cover creation of instrument configuration files in a later tutorial. So for now, we just have to select this one. The radiation the instrument uses is copper, so we can choose from one of many files that describe the characteristic spectrum of the radiation. Usually you can use chromium, copper, iron, molybdenum, cobalt. They appear multiple times for some reason. Copper is the right choice. And then I can also control the search iterations, how many refinement cycles or iterations it will perform. Usually 10 or maybe 15 is enough to determine if the phase fits or not. And I can restrict the angular range. For example, here I don't have any data, any peaks between 5 and 10 degrees. So it doesn't make sense to start the search at 5 degrees. I can just as well go to 10, which will already speed up the process a bit. And the upper end, all the important phases, they will have peaks here. So I can identify them by the peaks in this area. So maybe I can just go up to 46 degrees. I can see the cursor position down here. So this is 46 degrees. Again, that's enough to identify my phases, just to speed up the search and match process. Then it will refine. So when it refines each phase to this pattern, it will refine the unit cell, and I can control how loose or how strict the unit cell can vary. So I can completely disable refinement of the unit cell, so I only search phases that have peaks exactly at the measured position, or I can allow some refinement or a lot refinement. So usually strict allows a little bit of refinement, a little bit maybe chemical variation in the phase. So it still finds a good match, even if it's not precisely the same unit cell dimensions. Then I can also allow anisotropic parameters and sample height displacement, but usually for the first cycle, we don't want to check this. For the first cycle, we want to keep it fixed. And for the crystallinity, if the peaks were very wide because the material is nanocrystalline, I should allow some low crystallinity or even nanocrystallinity, so it's actually able to match the peak width. But this is a highly crystalline sample. I can easily see that the peaks are very sharp. We can resolve K alpha 1 and K alpha 2, so this is a highly crystalline sample. We don't want a lot of peak broadening to happen here. So now everything is set up correctly. We can just start the search match process by clicking the I symbol up here in the toolbar, run search match, and see what happens. it automatically switched to the results page of the search match module, and it starts filling or listing the phases that it tried to match to the measured data. And the list is sorted by a figure of merit with a color code, and the best match is always on top. So now it's done, and at the top of the list, the best matching phases are all tricalcium phosphate phases with slightly different chemical composition. One of them with some hydrogen substitution, another one with some sodium, the pure one, and one with some strontium. If we click on them, it will show that it will select it here in the reference structure list, and it will show the line positions, and they all look very good. There's almost no difference in peak positions. So we have to decide. So obviously it's a correct identification, and we have to decide which one we want to keep. We can also see that there are more peaks here. So there's another phase. Not all of the peaks are generated by tricalcium phosphate. So we can maybe just pick the easiest one, the pure composition for now. And we want to keep this phase, we want to pin it. So we click this button and it will be added to the pinned phases. And now when we run search match again, it will try to find something that matches the peaks that do not belong to beta TCP. So we just run it again, see what happens now. As you can see, to every match cycle, it added the beta TCP phase plus the one it is trying to match to the residual peaks. So it's now refining 2 phases in each cycle, and that's why it is slower than in the first run, where it only matched 1 phase. So the more phases we add, the slower this will become. So now all the different appetite phases are at the top of the list. Let's just check again the beta TCP. So we are now searching for phases, for example, matching this peak. And if we click on the appetite, hydroxyapatite monoclinic, or the hexagonal one, or a carbonate apatite. So they are all very close. So it's probably some kind of apatite. This one contains some copper. This one is calcium deficient. So we can maybe again just select the easiest hydroxyapatite, the hexagonal one, and also pin it. And now the question is there a third phase? We can run it again. But already now we can see that probably there's no peaks that do not belong to beta TCP or hydroxyapatite. Okay, so now at the top of the list there is again this calcium deficient hydroxyapatite, but we already have apatite in the pinned among the pinned phases. So it probably just has difficulties to decide which one fits better. So I think it doesn't make sense to have both the normal hydroxyapatite and the calcium deficient hydroxyapatite in the pinned list. So we will just ignore this. We already have apatite pinned. But the second phase, beta calcium pyrophosphate, we have to check. The strongest peak is this one here. If we hold the mouse pointer here, we should see a tooltip that's beta CPP, the 00-8 peak. So we have to check if this peak does belong to appetite, or actually it's a TCP peak. So this is a false positive match. Because all the peaks it thinks belong to beta CPP already belong to TCP or appetite. So we only have 2 phases in the sample. And to be honest, in a simple synthetic composition, I would come to this conclusion much more easily because I would already have an idea what is in the sample. So I would immediately check for my usual suspects, hydroxyapatite. I would zoom in and see, yeah, that's a good match. And same for TCP, I would maybe check the alpha phase. That's not a good match. Then the pure beta, and I would already know which 2 phases I have in my sample. But for a complex composition, especially if I'm looking, if I'm doing a residual search, if I'm looking for very weak peaks, maybe I don't see all of them due to peak overlap, then the search match module is very powerful and usually provides quite good results. The search match module also lists a preliminary quantification, so it shows the fraction of these phases, but this is not very useful. It's not very accurate. So sometimes I prefer to clean up this list. It shows quite a lot of information. If we right click on the header, we can hide the columns phase and fraction. So we only show the file name and the figure of merit. And so usually I also keep the source. I will explain later on what this means. So these are matched phases. We can also run search match again on a complete refinement project, and then it will show us which phases come from this match process and which are the ones we added manually to the refinement project. So for now, this looks a lot cleaner, so I prefer to hide the columns I'm not interested in. Now that we know the phase content of the sample, we can create a refinement project and do a full Rietveld refinement in order to determine the phase quantities and crystallographic parameters. But this will be covered in the next episode, so be sure to come back soon and check it out. If you like this episode, please give it a thumbs up and subscribe to the channel, and I'll see you soon.